Our first speaker is Aline Michel. She presents Galois fractures in preordered groups from UCL.
Okay, so good afternoon and thank you very much for being here. So my talk is about categorical Galois theory. So categorical Galois theory is a generalization of classical Galois theory. It has been introduced by George in the 19th. And the goal of my presentation is to present two different Galois structures in the category of preordered groups, and more precisely to describe trivial central norm extensions with respect to these two categorical Galois theories. So this is a joint work with Mathématique. So first of all, I will just quickly remind some notions about the category of preordered groups. So first of all, what is a preordered group? So a preordered group is given by a group and a preordered relation are written in this way, which is compatible with the addition of the group. So in the sense that if you have A smaller than C and B smaller than D, then A plus B is smaller than C plus D. So here we use the additive notation, but the group G is not necessarily abelian, and I will look at the preorder relations relation that is both reflexive and transitive. So the prototypical example of a preordered group is given by the group of integers with the usual order. So this preordered group is actually a bit special for two reasons. So the first reason is because the group of integers is actually abelian, and the second reason is that the preorder is actually here a partial order because it is antisymmetric. So we say that this preordered group is a partially ordered abelian group. And we see in this presentation that both partially ordered groups and preordered abelian groups will play an important role. So given two preordered groups, morphism between them is now given by a group morphism between the two underlying groups of the two preordered groups, which preserves the preorder in the sense that if you have A smaller than B in the group G, then F of A is smaller than F of B in the group H. So in other words, morphism of preordered group is just a preorder preserving group morphism. And if you now take all preordered groups and morphism between them, this defines the category of preordered groups, which will be denoted this way in this talk. So now the category of preordered groups is actually isomorphic to another category that I will describe right now. So the objects are given by pairs, GPG, where G is a group and PG is a subunit of G closed under conjugation in G. And the link with the definition of a preordered group is that this subunit PG is actually the subunit of positive elements in G. So this is why we call this subunit the positive pole of G. Now, given two such objects, so GPG and HPH, a morphism between them is given by a group morphism F between G and H, such that F of PG is in PH. So actually this condition means that F restricts to the positive cones, so that alternatively we can see this morphism as a pair F bar, where F is a group morphism and F bar is a monoid morphism, making this square root. So this category is isomorphic to the category of preordered groups, so that we can use this definition as an alternative definition for the category of preordered groups. So now it has been studied by Clementino, Martin Serra, and Montoli in 2019, and they proved that it is both complete and co-complete. In particular, the limits are really easy to compute because it suffices to take the limits at both levels, at the level of groups and then at the level of monoids. For example, if you want to take the limits of FF bar, the kernel of FF bar in the category of preordered groups, it suffices to take the kernel of F in the category of groups, then the kernel of F bar in the category of monoids, and this gives you the kernel of FF bar in the category of preordered groups. So the limits are a bit more complicated, but it is still complete. It is also a normal category in the sense of Zuhar generality, which means that it is a pointed regular category in which any regular homomorphism is the co-kernel of its kernel. So it is regular, unfortunately it is not bar-exact, but it still keeps an interesting property of bar-exact categories, namely the fact that effective isomorphisms exactly coincide with regular homomorphisms. And a morphism FF bar in the category of preordered groups is a regular epimorphism precisely when both F and F bar are surjective. So this means that the class of effective isomorphisms have a really easy description in the category of preordered groups, which is not the case in general in a non-bar-exact category. And we will see actually that in categorical Galois theory, in particular, it it is really useful to have a simple characterization. So it is not bar exact, and Clementino Martesonera and Anthony also put that it is not protomodular, and with Magnum also put that it is not subtractive. Okay, so now let's start with the first categorical Galois theory I would like to present. So we will see that it is induced by a Galois structure which is absolute. So I will explain what it means just in a few minutes. So for this, consider first the full subcategory of partially ordered groups. So the objects of this category are just given by preordered groups endowed with a partial order. So for example, the group of integers with the usual order. And with the alternative definition, we can see such objects are as pairs GPG, where the positive pole is a reduced monoid. So PG is a reduced monoid means that the only element in PG having also its inverse in PG is actually the neutral element of PG. So now let's define a functor to this full subcategory of partially ordered groups. So we consider any preordered group, and we have to transform it into a partially ordered group. So we need to transform this submonoid into a reduced monoid. So the idea is to consider this subset, NG, which is the subset of elements X in G, such that both X and minus X are in PG. And the idea is to somehow quotient PG by NG. Of course, we need to be careful when we take the quotient. And actually what we remark is that NG is a normal subgroup of G, so that we can quotient by G by NG. And now what we do is that we take this composite, so inclusion followed by the quotient, and we take the regularity monofactorization in the category of monoids, so that we get eta G of G, which is a submonoid of G quotient by NG closed under conjugation in G quotient by NG. So this pair is actually a preordered group, and precisely we can prove that it is a partial ordered group since eta G of PG is reduced. So this is the definition of I of GPG. And we can prove that I is actually a left adjoint for the inclusion factor H, and that if we consider the classes of all morphisms in preordered group and power group, then we get a Galois structure. So I want to recall what is the general definition of a Galois structure. Basically, it is given by an adjunction and two classes of morphisms in the two involved categories, and these morphisms are called extensions. And when the classes of extensions are the classes of all morphisms, as it is the case here, we say that the Galois structure is absolute. So this is why I used this notation gamma abs. It's for absolute. And this Galois structure gamma abs is actually admissible. So what does it mean for a Galois structure to be admissible? So if we have a Galois structure, so an adjunction plus two classes of extensions, a Galois structure gamma is said to be admissible when the left adjoint F preserves all pullbacks of this form. So where eta B is the B component of the unit of the adjunction between the factor F and the factor U, and phi here, the morphism phi is any morphism in the class Z. Now, we have a general result which says that if C and F are two categories which admit all pullbacks, the factor F is a reflector and the Galois structure gamma is absolute, then we have this equivalence. So gamma is admissible if only if the reflector is semi-exact. And it turns out that we are in such a situation since the two categories here are both complete, so in particular admit all pullbacks. And the factor I is clearly a reflector, and here we have an absolute Galois structure. Now, actually, this factor I is induced by a torsion theory and the normal category of preordered groups. So by a general result, we can deduce that I is actually a semi-exact reflector, so gamma abs is admissible. So it is admissible, and we can now describe trivial and central extensions. So I will quickly recall the general definitions. So for a Galois structure gamma which is admissible, a morphism F in E, so an extension, is said to be a gamma's trivial extension where the naturality square involving F is a pullback. It is said to be a gamma central extension when there exists an effective morphism P in E with the same phenomenon as F, such that the pullback of F along P is a gamma trivial extension. So this means that there exists P, an effective isomorphism, such that if we take the pullback of F non P, then the first projection pi1 is a gamma trivial, which means that the naturality squared involving pi1 is a pullback. So I want to recall what is an effective isomorphism. All you need to know is the description of effective isomorphisms in the category of preordered groups, but I already told you that it is just given by morphisms F bar, such that both F and F bar are surjective. Okay, and now we have some special kind of gamma central extensions, which are called gamma normal extensions, and these are given by effective isomorphisms, such that the pullback of F along F is gamma trivial. Okay, so now with respect to our Galois structure gamma apps, we have found a description of both trivial and central extensions. So for a morphism F bar in the category of preordered groups, so from GPG to HPH, we have that F bar is a gamma apps trivial extension if and only if the restriction of F to NG is a group isomorphism. So where NG is this normal subgroup of elements X in G such that both X and minus X are in PG. And it is a gamma apps central extension if its kernel is partially the group. And so this is a really nice description because it is really simple. And what is nice also is that these results can be generalized to V groups for V commutative unital and integral quantal. So for example, this can be generalized to low-layer metric groups, low-layer ultra-metric groups, or also probabilistic metric groups, for instance. So for more details, you can refer to this paper. Okay, so now let's see a second categorical Galois theory in the category of preordered groups. And this time it will be induced by a Galois structure which is not absolute. So the class of extensions won't be the class of all morphisms. So for this, let's first recall that in the category of groups, there is an admissible Galois structure, gamma A, which is induced by the abilization factor. So the abilization factor which sends any group X to its quotient by its derived subgroup. And with respect to this admissible Galois structure, we have that normal and central extensions coincide. So we always have that normal extensions are central, but the converse is not true in general. Here it is the case, and they coincide with regularity morphisms such that the kernel is in the center of the domain. So these are called algebraically central extensions. So the goal of this part of the talk is to generalize this well-known categorical Galois theory to the context of preordered groups. So for this, we first consider the full subcategory of commutative objects in the category of preordered groups. So this is actually the category of preordered abelian groups, so the category whose objects are preordered groups such that the underlying group is an abelian group. And now let's define a functor to this subcategory. So again, we have GPG, any preordered group, and we have to transform it into a preordered abelian group. So we need to transform G into an abelian group. So what can we do? We can use the abilization functor so that we get an abelian group. And now we proceed as before. So we take the regularity monofactorization of the composite. And this gives us a preordered group, since we can prove that eta G of Pg is a submonoid of above G close to the conjugation in above G. And in addition, it is a preordered abelian group, since above G is an abelian group, of course. So this is the definition of C of GPG. And C of GPG is a reflector. And now, if we consider the classes of regular morphisms, we get an admissible Galois structure, gamma C. So here the classes of extensions is no longer the classes of all morphisms, but the classes of regular morphisms. And actually, with respect to this Galois structure, we have found a purely algebraic description for the class of normal extensions. I won't give you the description because I don't have enough time, and I would like to make you realize that, so this is the full subcategory of commutative objects. Now, commutative and abelian objects coincide in the category of groups, so these are given by abelian groups, but in the category of preordered groups, it turns out that these are not the same. So this suggests now to go further, so now to consider the full subcategory of abelian objects. So an abelian object in the category of preordered groups is given by a preordered group GPG, where not only G, but also PG is an abelian group. So actually, the category of abelian objects is then given by the category of monomorphisms in the category of abelian groups. So now the idea is to define a functor from preordered group to this subcategory, and for this we consider the following composite. So here we have the functor C we have just seen, and here we have the functor A, which is defined for any preordered abelian group GPG by A of GPG is equal to G group of PG, where group of PG is a group completion of PG, also called the prototypic group of PG. So the composite F is then defined as follows. So for any preordered group GPG, we first apply the functor C in order to get this preordered abelian group, and then we apply the functor A in order to get this preordered group, which is an abelian object in the category of preordered groups. It turns out that this functor F is actually a left adjoint for the inclusion functor U, and we can see that just by composite. So we already know the adjunction on the left, and actually the adjunction on the right is induced by the adjunction between the group completion functor and the forgetful functor between the categories of monoids and groups. So indeed, if we come back to the definition of A, we can see that A only acts on the positive cone via the group completion functor. It doesn't act on the group G. So it is easy to see that this adjunction is induced by this one. And then as a composite of two adjunctions, we have then F is a left adjoint for the inclusion functor. Actually, this adjunction here has been studied by Montoli, Modello, and Van der Linden in 2014, and they have proved that this adjunction induces an admissible Galois structure, and with respect to this Galois structure, they provided a description for central and normal extensions. So this part, so their paper was really useful for this part of the talk, of the research, more generally. So now let's consider the classes of regular epimorphisms in preordered group and mono-arc. Then we can prove that we have a Galois structure, and this Galois structure is actually admissible. Why? Because we can see gamma as the composite of two admissible Galois structures. So the first one induced by this adjunction, and the second one by this adjunction. So as a composite of two admissible Galois structures, which are compatible in a way that I won't explain, we have that gamma is admissible. And it turns out that with respect to gamma, we have that normal and central extensions are the same. And so here is the description of normal and central extensions. So for FF bar, which is an extension, so I recall that an extension is a morphism in the class E, so a regular epimorphism. So for FF bar, a regular epimorphism in the category of preordered groups, we have that FF bar is a gamma normal extension, if and if it is a gamma central extension, if and if these two conditions are satisfied. So the first condition says that F as a group morphism is an algebraically central extension, and the second condition says that F bar is what we call a special Schreier surjection in the category of monoids. And in this case, in this precise case, it turns out that this means that for any xy in the kernel pair of F bar, we have that y minus x is in PG. So this is a very, very easy description for these two classes of normal and central extensions. So this is really nice, and actually this provides, this achieves our goal because we have found what we wanted to have. So we have found a full subcategory of the category of preordered groups, as well as a reflector to this subcategory, which is a generalization of the abelianization functor, in the sense that it is the functor to the subcategory of abelian objects in the category of preordered groups. And this adjunction is suitable in the sense that it induces an admissible Galois structure. And with respect to this admissible Galois structure, we have seen that central and normal extensions are the same, and we also provided a description, a purely algebraic description for central and normal extensions. So as a conclusion, I presented two different categorical Galois theories in the category of preordered groups. one which is induced by a Galois structure which is absolute, and the other one, which is this one, which is induced by a Galois structure which is not absolute. So this is all what I wanted to tell you today. So these are the references for my presentation. So this paper for the first Galois structure, this paper for the generalization to V groups, and this paper for the second Galois structure. So thank you very much for your attention, and thank you.
Thank you, Aline, for the presentation and for being so sharp in the time. Really. And so it's time for questions or comments. Anyone? Yes, please.
In the beginning, you mentioned that your category is not subtractive, and I'm wondering why it's not subtractive, because the category of groups is subtractive. So why the addition of these partially ordered implies that subtractive failed?
Actually, the idea is that you have monoids in a positive form, and so somehow it prevents the preordered groups to be subtractive.
It is not subtractive, but it is weakly multi.
Okay.
Great.
So that's the part that keeps the structure.
Thanks.
Please.
So how do you see this work continuing? So, like, how would you, like, are you looking for more Galois structures, or are you going to work? How do you see?
What I intend to do is to then compute the fundamental group on the basis of this description. And also maybe to see if this part of the talk is also generalized, can be generalized to V groups. Because the first Galois structure has been generalized to V groups, this one not. So maybe this would be representative to see if it's possible.
Time for more questions, if any.
So I would.
Yeah.
So about generalizing the V groups, do you think, have you done work to that direction, or is it like, so what's your intuition about it? Do you feel like it's going to work, or it's not going to work, or it's kind of very open?
I think for you have a composite here. So for the first part of the composite, I think it shouldn't be so difficult. But for the second part, I used this paper, so it should be a bit more difficult because it won't be possible to use this paper again for V groups. But maybe I have some ideas of what the description should be. But it's purely an idea, it's not rigorous.
Have you discussed with Kim van der Linden or the other people in the paper about this, about how that paper could be modified to your purposes?
Sorry?
Have you discussed with the writers of the paper about this generalization?
This paper about
Okay. It's okay? So you can discuss it. Some here. So I don't think there are questions. There is one.
It's not a question, I just want to add to this discussion. I think it's a good moment where good work is completed, and let us not put pressure what you do next. But it's very nice, thank you.
Okay. Last question.
A small question. You have two assumptions here. Do you have some kind of morphism between these assumptions? Like you can forget preordered groups down to groups and mono add to add.
I don't really understand the question.
Do you have a pair of functors between them? There's a forgetful.
Yeah, because so like you could make every group into a preordered group by taking the trivial order.
Yes.
Okay, so these commute with the left and right.
It's generalized.
Okay, great.
Okay. So let's thank you again. have 5 minutes.